All right, this video is on vapor pressure and how vapor pressure relates to intermolecular forces, and then a little bit of a discussion on boiling point. And all of these things, of course, are related. Okay, so before we start with vapor pressure, I want to talk about pressure real quick. And pressure, which is something that we talk about a whole lot when we get to gases, pressure is caused by the collisions of gas molecules. So the key word here is collisions. So if gas molecules are colliding with each other, or if they're colliding with the walls of the container that they're in, those collisions create a pressure. Okay, so anytime we have gas, we have pressure, and that pressure is caused by collisions. More collisions, more pressure. And we'll relate everything back to that. So there's a particular type of pressure that we talk about in this chapter, which is called vapor pressure. And so what we're discussing here is if we had a container. Now this is going to be a closed container. So a beaker with a lid or a water bottle with a cap on it. Okay, but that's important that it's closed. And so what happens is we have these liquid particles right in the container, which eventually will gain enough energy from the air, from the desk that they're sitting on, whatever, to evaporate. And so those liquid particles will evaporate and turn into gas particles. They're stuck inside the container because it's closed. There's a lid on it. And then those gas particles collide with each other and the walls of the container, creating a pressure. And that pressure is called vapor pressure. And basically, it's just a pressure above a liquid. Now, this only happens in a closed container because, as you might imagine, in an open container, while evaporation would still occur, those particles would not be confined, and then those particles would just escape, like, into the air, and there would really be no vapor pressure to talk about. So we're talking about this occurring in a closed container. Like we said, a water bottle is a great example with a lid on it. Okay, so what's really happening kind of at the molecular level during this idea of evaporation and creating a vapor pressure? So this is kind of the second point of discussion here, and it's actually a very big one. So what happens in our closed container is that as the particles gain energy, evaporation occurs. So given enough energy, these liquid particles, like we just talked about, will evaporate and turn into gas particles. Okay. But maybe unknown to you is the fact that then those gas particles will release some energy and turn back into liquid through the process of condensation. So what eventually happens is that we have evaporation occurring just as condensation is occurring. And eventually we say that the rate of evaporation is equal to the rate of condensation. And this idea of the rates being equal is discussed as something called an equilibrium. Now, equilibrium is an entire chapter in chemistry, and it's a huge one. But in this case, we're talking about these phase changes occurring not only at the same time, but at the same rate, the same speed. So the number of particles that are in the liquid form and evaporating to the gas, that same thing is occurring as the gas is condensing into a liquid. So to the viewer of this capped water bottle, it sure looks like nothing is happening, when in reality, particles are evaporating at the same rate that they're condensing. And so there's always something happening in that capped water bottle, even though it looks to us just like it's a bottle of water. And this idea of equilibrium, of course, has a root word, which is equal. And so equilibrium is defined as a state of balance. And if you know anything about equilibrium within the body, you might know that you have an equilibrium that's established in your ear. And so sometimes when people are sick, that equilibrium is thrown off and that state of balance is disturbed, and people get dizzy because they've lost their state of balance, which is an equilibrium. Okay, so this is a huge discussion, and right now we're only entertaining this idea, talking about phase changes, that we have liquid going to gas just as we have gas going to liquid. One way to show that very simply would be to say that not only is the liquid turning into a gas, the process of evaporation, but the gas is turning into a liquid, the process of condensation. And so it's the first time that we've seen this double arrow, or double-headed arrow. And the spoiler alert here is that not only can phase changes reach equilibrium, but so can chemical reactions. And that comes later in this course, but there's a whole discussion of equilibrium occurring within a chemical reaction, which is something that we've yet to talk about. So that comes at a later date. So the big connection that we want to make here is what's the connection between this idea of vapor pressure and strength of intermolecular forces. And so that's going to be the big takeaway in this. So if we go back to my top picture and we think about what's occurring here, that these liquid molecules are evaporating, turning into a gas, and it's the gas that then creates the pressure. So if we think about strength of IMFs and how this affects vapor pressure, we can come up with a relationship. So if we have a liquid whose particles evaporate readily, like they evaporate quickly, that would be a compound that has low intermolecular forces, or weak intermolecular forces, right? If evaporation is occurring quite readily, then the strength of the IMFs is pretty low. So if we have low IMFs, rapidly occurring evaporation, we have lots of particles up here, which is going to give us a higher vapor pressure. And so hopefully you just heard that there's the proportionality, and that they're inversely proportional. So the stronger the IMFs, the lower the vapor pressure. And so I want to say that one more time, and let's box this and star it a couple times. So, oops. Oh, goodness. So let's go back up. Why? I don't know. Jeez. Let's go back up to the top and talk about why that is the case one more time here. Okay, so again, we'll do it both ways. If I have a liquid that has very strong intermolecular forces, that means evaporation is not going to occur very quickly, and it's not going to give you a lot of gas particles. So strong or high intermolecular forces is going to give you a small amount of gas particles up here, small gas particles, small collisions, low pressure. So there's the higher the strength of the IMFs, the lower the vapor pressure. Or vice versa, if this has low intermolecular forces, the particles are going to readily evaporate, more particles, more pressure. Okay, so it's an inversely proportional relationship. All right, a couple more terms here to talk about, and one of these terms is the term volatile. And a lot of students have a misunderstanding about this word. A lot of students tend to think that the word volatile means reactive or even explosive or dangerous, and actually it means none of those things. A volatile substance is a liquid that readily evaporates or easily evaporates. And so I'm sure that you might guess we're going to connect this to IMFs. Because if we have a liquid who evaporates pretty quickly, a great example would be rubbing alcohol, then that substance has low or weak IMFs. Because compare that to something like water, who does not readily evaporate, would not be called volatile. Water has very strong IMFs. So volatile liquids have fairly weak IMFs. Great example is rubbing alcohol. How could we get something to evaporate quicker? By giving it energy, by raising the temp, right? And so we could have a discussion here about temperature affecting the rate of evaporation. Raise the temp. You raise the evaporation rate, which if we're in a closed container, you would raise the vapor pressure. So lots of air hose in this discussion, talking about the relationships here between what's it mean to be volatile, what's that mean in terms of strength of IMFs, and then how does that affect vapor pressure. All right, so one more thing to kind of connect all of this. We know that when we talk about IMFs, we're often asked about boiling point, right? And we've made that connection in the past, that something that has stronger IMFs is going to boil at a higher temperature, because it's going to take more energy to separate those particles and to break those IMFs. But we need to do a little bit of a dive into boiling point as a whole and talk about it. So, of course, we understand what happens when boiling occurs. We're changing from a liquid to a gas, and we're breaking those IMFs. But the boiling point of something is actually defined as the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. And so this being the key, that boiling point depends on atmospheric pressure. And if you want to talk about that in terms of location and where you are on Earth, then we can expand that one step further and say that boiling point is going to depend on what elevation you're at. And that's because if you decrease the atmospheric pressure, then you're going to decrease the boiling point. And then the opposite of that is true. If the atmospheric pressure is higher, it's going to raise the boiling point. So then how did we decide that water boils at 100 degrees Celsius? Well, what we are now saying is that water can boil at numerous temperatures depending on what the pressure is. And so how did we get 100, right? So scientists had to pick some kind of standard across the board. And so what they did was, first they referred to it as the normal boiling point. And the normal boiling point is the boiling point at sea level. Where the atmospheric pressure is what we refer to as 1 atmosphere, or 1 ATM is the abbreviation. Because what we're saying is if we change atmospheric pressure, which changes with elevation, then water can boil at temperatures that are not 100. And so 100 comes from the boiling point at sea level. So let's talk about what happens in Denver. So Denver has a nickname, and the nickname is the Mile High City. And it's not by chance that it's called that. Denver is extremely high in elevation. And most people, when they're talking about Denver, they'll refer to a phrase that is the air is thin. And I hate this phrase because air is not thin, nor is somewhere else is it thick. Okay, but what they mean by that is there are less particles in the air at that elevation. And so less particles, as we talked about earlier, means less collisions, which means less pressure. And if you know anything about when the football teams go to play in Denver, they often have to wear the oxygen mask on the sideline or during practice while they're getting used to the fact that there's less oxygen because of the elevation difference in Denver than where they're used to playing. So let's talk about water in Denver, and this is so interesting because Denver is so high in elevation and the pressure is low enough that we actually see a difference in the boiling point of water. In Denver, water boils at about 95 degrees Celsius, and that's because the atmospheric pressure is lower. Could we get water to boil at an even lower temperature? Yes, we could, but you'd have to decrease the pressure significantly. And so we could do that in a lab with a vacuum, right? Some kind of system where you're pumping out air, decreasing the pressure, and you could theoretically get water to boil at pretty much any temperature you want by manipulating the pressure. And that might be something that you didn't know, nor have you ever thought of. Can you get water to boil when it's not hot? Yeah. But you would have to decrease the pressure significantly, and you would need some kind of vacuum situation to do that. Now, for the biggest question of all, when students find this out, they say things like, wait, so are you telling me that if I went to Denver, my macaroni and cheese pasta would cook faster? Right? Well, in Denver, your water would get to boiling faster because it's going to boil at 95 instead of at 100 here. So it would get to the boiling temperature faster, but then hopefully you remember that once something starts to boil, the temperature no longer changes. And so while in Denver your water would boil faster, it would stay 5 degrees cooler, and theoretically it would take just slightly longer to cook that pasta. And so that's a silly and kind of funny thing to think about, but it's true that while you would hit boiling first in Denver, because the temperature does not change during boiling, because now we know all of that energy is going into breaking the IMFs, it would actually take longer to cook the pasta. So there you go. So this was a discussion of vapor pressure and IMFs, and we had to link boiling point in there because we know that when we're talking about IMFs, we're talking about the boiling point of something.